Ladies and gentlemen, welcome to the first talk of this session. Our speaker is Professor Ming Ling. She is currently a distinguished university professor, Barry Mirsky, and Capital One Innovate Endowed Professor at the University of Maryland at College Park. Professor Lin is a leading expert in computers, animation, and computer graphics. Today, she will present her talk entitled Learning the Dynamic World. Let's welcome her.
Thank you for the introduction. Okay. So hopefully you can see my slides. I'm looking at the full display mode. So I'm going to talk a bit about learning the dynamic world. And the dynamic world I'm talking about is actually the physical world that we live in. Here are just a few examples. What we are trying to do here is to learn the physical intelligence through differentiable physics as an inductive biases for learning. And also, we are looking at how can we do the learning in a more intelligent way. We would like to be able to take advantage of the model. So we call this model informed learning to solve some physical problem in the real world. This might including, okay, what's the property of a fabric? Model-based RL, reinforcement learning, or control of autonomous systems like autonomous vehicle and self-driving cars. And so here are just sort of some of the examples. And our whole idea here is that we would like to have this iterative combined loops where we have a model which is then being incorporated into a deep learning neural network, which then provide the data-driven framework to drive the physics simulation, and then iteratively use the physics model to combine with the learning to go into this iterative feedback loop that keep going and going. This is a far better and a more efficient way of doing machine learning because we actually are using some existing work as a prior. And this new paradigm is largely driven by the very fact that we are living in a very exciting time where we have data driving the revolution of computing. The availability of data is in every single phone and it's everywhere, from 2D to 3D, from images to drawing to painting to text to audio to video to medical record, let it be CT scan, ultrasound images, MRI, patient records, or 3D geometry and model, or motion captures, or simulation data, or even meta information such as like the document, the social media, the web traffic, or the sensor data such as satellite information, the traffic information, the environmental monitoring, the sensing that we get around us, or any kind of representative sample of all different types from all different sources. AI and ML offer really a very exciting new opportunity, but it's also a lot of compute. And we have a lot of these data that enable these exciting opportunity. So what do we do? I would like to say learning is really all about reconstruction. It's a way of synthesizing information to predict how our world will evolve. We might have the record of the past weather, and thereby we can predict what the weather is going to be like in the next 1 hour, tomorrow, or the day before, or the day after, or a month into the future. And so that is a kind of prediction we would like to do. This is not just limited to the natural phenomenon. It actually also is applicable to stock market pricing. And it's the same kind of dynamics that we are seeing when we see what's going on, in the stock market. The price of each one of the stocks fluctuate over time because there actually are triggers that we can use to predict how a particular phenomenon or the variation of anything through time. So in my view, what we are really interested in doing And what machine learning is really offering us is a way of creating what I call the ultimate metaverse. A metaverse is a reality that bridges between the digital world and the physical world. And what we want to do is really create the ultimate metaverse that allow us to seamlessly transcend these boundaries between the digital and the physical domain and the world that we live in. But it also allow us to create the impossible. It allow us to predict how a system evolved, the possible future events, or the demand of a commodity or stocks pricing, how it fluctuates. It also offers us a virtual playground for the students, for the research scientists, for the engineers, and also a meta lab for testing our concept, a hypothesis, for designing new products, for validating and prototyping a new, um, you know, systems. So it enables many possibilities that otherwise may be difficult. And to do that, what we really want to do is to capture and reconstruct the dynamic world by bringing the physical universe into the metaverse. And that's what I'm going to focus on this talk. So what are some of the challenges? There are really two types of challenges, I would argue. The first one is on data challenges. And the data challenges that we are addressing and we are looking at is the diversity of the data, their representation and their format. It could be 2D, 3D, undimensional. It could be text, number, images, audio, video, or abstract concept. It could be geometry, physics, appearance, or behaviors. And the volume of the data will naturally command the amount of the associated computation required. And when we compute this much with this much data, we also have to worry about how do you cool down the heat generated by the GPU or these computing cluster? What about the electricity consumption? There are some cities where the data center is taking up 50% of the whole entire city. Just think about that. The data centers are taking up more than 50% of the electricity consumption of a given city. That's today. What about tomorrow? What about a month from today? What about a year from today? And so we need to think about what these implications are. And then we also need to worry about where do we store all these data? How much memory consumption there will be. Now, that's just about sort of the compute associated issue. But there are also the very fact that these data intrinsically are encoding biases. How we might have captured them. They may have noises that are inherent associated with all type of sensing. And there's also uncertainty because these data are capturing a certain phenomenon and the sensor have noises. So there is a certain level of uncertainty regarding the level of accuracy that we don't necessarily know. And then last but not least is most of the time, the data we capture are incomplete. So I started by asking the question, how much data do we need? Is more really better? And I would argue, no, absolutely not. More is not better. Why? Because you can compute the same thing over and over again. You already know. You don't need to compute the same thing over and over again. Remember what I say, the volume of the data. If you have the same data that give you the same information, it doesn't help. We're talking about large language model. We consume more information about language. If it's all in English, it doesn't help. We may wish to create a large language model for Chinese. We may wish to create a large language model for Spanish and all different language, or something that are very, very rarely used, but it doesn't exist yet. But the point here is we also have the situation where we actually have incomplete collection of data. For example, most of autonomous vehicle like self-driving car, they are operating based on the data they already collected. And most of those data were collected when it's sunny and it's bright, um, it's safe. No driver is going to put themselves in danger or put their life at risk to collect data during the accidental scenario. So what we have is the missing data when we have an accident often. And and then there is also the issue of if we do all this learning, the world we live in actually have a lot of categorization, have a lot of ontology and a taxonomy. And these categorization and ontology and taxonomy create context. It helps us classify information. We don't have enough of such in our reasoning because they also help reasoning. They create a hierarchy of information. And then there is the issue as of how are we capturing these data? Under what context are we capturing these data? Are we capturing them in a control process or are we capturing them these data set randomly? And it matters because this determines the kind of data that we capture. Are they biases? Are they did it consider some of these issues such as uncertainty, such as incompleteness, and such as noises? Then there is other challenges. So those are the data challenges. There are also technical challenges. And these technical challenges comes from the very, very excitement of generative AI. Every single big tech today, almost every single one of these big tech companies nowadays have a group on generative AI. What is a generative AI? Well, it's a process of generating synthetic information using AI. My joke is I also work in computer graphics. And generative AI is what computer graphics does. It creates synthetic images, it creates synthetic motions, it creates synthetic 3D world. So whether you have a generative AI or you have other data-driven methods, what a lot of time what they offer are empirical model. These are prediction based on data. And they are created empirically based on experiments. A lot of time, we don't always know if they are correct. A perfect example is like diffusion. Diffusion methods are really cool. You can generate a lot of visual effect. But often, they also generate artifact. They also generate information and images that was not part of the real world. We don't know exactly where they come from. They hallucinate. And we also have other problem that we are dealing with, which is the very fact that we have machine learning or neural network systems that are like a black box, meaning that we don't always know how to interpret the results that we have and how we get there. Can we explain? Do we really know what's the underlying process? We don't. They were created. The prediction was done by these neural network and doesn't always have an explanation. And that is troubling for people who are scientific minded or engineers who want to know exactly what are we getting. Last but not the least is the very fact that the model and the prediction that we have was based on incomplete sets of observation. Just like the previous slide I mentioned, we have incomplete data. And if we have incomplete data, we have incomplete observation. It's a subset of the reality. So what do we learn? Some people say garbage in, garbage out. For the same reason, if we have incomplete information, what we learn and what we predict, it's not going to be complete. So because of all these reasons, all these technical challenges, what we learn often as a result of these technical challenges is that they are not generalizable to unseen domain, unseen scenario, or they don't transfer across task. If a robot know how to pick, a robot does not necessarily know how to turn and manipulate. Also, it's not robust with respect to the input or the domain. They can vary. It may not work under different lighting. The car will drive when it's sunny, but it may not able to drive when it's raining, when it has snow, when it has fog. So those are the kind of issue we have to deal with. And lastly, it's not the least, but it's something that we as a community and just as researcher and scientists, we need to start thinking about is that learning purely from data can be extremely costly. Every single piece of data that we have need to be processed. So training is at least linear. And as a computer scientist, I used to joke, we like hierarchical representation. We like hierarchical data structure. That, however, is not how these neural networks are being structured. They are not. They are actually very flat. And so it's going to be always linear cost. If you have a hierarchical structure, your computation becomes log n. And so if we need to think about exactly what are we doing and what are some of these challenges that AI and machine learning has presented for us, how can we learn the dynamical world? The dynamical world is far, far, far more complex than language. Language is 1D. Images are 2D. The real world we live in is 3D. And if it's changing and it's moving in time, that's 4D. So the complexity of learning goes up. And that's why we need to be thinking going forward. What does it mean when we have to learn about the physical world we live in? So I'm going to talk a bit about sort of some of the projects that we have been working on. The first one is differentiable physics simulation. This is a very exciting direction, and I'll show you a few examples. And the other one is the data-driven simulation and reconstruction from video. And this is really a step toward from real to sim. And we'll talk about autonomous driving using simulated accidents. And this is address the issue of the very fact that we often have incomplete data that we are capturing from the real world. How can we fill in that gap? Through simulation. Now, after everything I talked about, one of the things that is really critical is for us not to forget we are creating these machine learning systems, these AI systems, not because we're creating them for AI, not because we are creating them for machine. We are creating them to interact with a human. So we need to think about human-centered AI system. And so each one of us have different personality. So I will illustrate this concept by looking at personality condition driving behaviors prediction for autonomous driving. And then again, we need to also address the issue of the robustness. The very fact that we learn and we capture data when under one condition, but these systems need to operate under a different condition. How do we deal with different domain shift? How do we deal with different conditions? Okay, differentiable physics. What we're doing here is really to propose this paradigm of learning the physical world with a differentiable simulation in geometry, whether it's in vision, whether it's in language, whether it's in robotics. This kind of paradigm can significantly transform the way that we learn the world around us. And essentially what we are saying is take the existing simulation or the geometry model as a layer of a neural network and bring it into the neural network and treat it as a prior. And so what we are doing here is using the differentiable physics simulation is basically taking and using the physics simulation as an inductive bias for learning algorithm. And we can use the power of deep learning to solve the physics problem in return. And use this couple loop, which I talk about at the very beginning. Oops, sorry. And and this has a lot of implication because when you do this, you can actually use this neural network and trainable network coupled together with your differentiable simulation. You can actually calculate the gradient, which you can then back propagate through your network. And then you can use that to estimate. So the gradients is, what you can do in your optimization and your learning to learn about what's the material property. Um, and some of these example could be like, what's the coefficient? What are the stiffness of the fabric? Can you use the back propagation or gradient to control your system? Can you use the gradient for model-based reinforcement learning? And so those are the kind of concept. And in fact, we have used such a concept and applied to many different areas that you see here, whether it's robotics, whether it's computer graphics, or computer vision, or even quantum computing. We have shown by using this paradigm of differentiable physics, we can accelerate the learning by at least 10 times. Sometimes we can accelerate it 3 order of magnitude. That means it's 1,000 times faster for learning these physical system, very complex physical system. And these work, as I have shown here, we have done it for quantum computing, for traffic management, for fluid simulation, for simulating soft body, for simulating articulated body, for drone, for rigid body, for robots, you name it. We have applied this to many different areas. And we have shown this has applicability across many different domains. And these are just sort of some of the examples that we have tried. They also are very scalable. So their interaction between a different object could be order and square. With this approach, we can actually accelerate the computation significantly more and to reduce the computational complexity down to linear. And this is just sort of some of the examples that we have also applied to an articulated robotic link, a running 4-legged robots, or a car, which needs to hit a target. You can control the physical system. You can enhance your reinforcement learning by doing far better sampling. And you can also estimate the physics parameter, like in the car, driving on the carpet. We can learn what's the coefficient of friction from these systems. Now, we have also applied this concept to autonomous driving or hybrid differentiable traffic simulation, where we are looking into how a combination of different traffic simulation together combined with a machine learning algorithm can actually help us manage traffic and control traffic.
Introducing our novel differentiable hybrid traffic simulator. Our simulator supports very large scenes in real time as we use a hybrid approach of macroscopic and microscopic methods. Note that every component is fully differentiable, including conversions between different methods. We can use the gradients to solve a variety of traffic problems. We can reduce congestion. We can estimate parameters in the simulation. And we can train a pace car to control other vehicles.
Okay. So we have also developed the simulator for traffic simulation, and we made it differentiable, and we use it for traffic management and traffic control. And you just show a very, very, very brief demonstration of that.
Introducing our
so those are differentiable physics simulation. As I already mentioned, we have applied this to many different domains. And the other area which we have been looking at is data-driven simulation and reconstruction of the real world directly from videos. And this is a example of actually YouTube video, which we downloaded from the web. We are able to track the pedestrians and reconstruct the scene and reenact it as a simulation, a data-driven crowd simulation. Then we can ask the what if question. Same scenario as you seen in the video, but now we can ask, what if there is an explosion? How will people react? So these are the kind of things that more and more people are interested in doing. Um, and the other example that we have done is learning the fabric material directly from videos. So what we have done here is we have developed a neural network, which is a combination of CNN plus LSTM. And the CNN will be extracting the image features. Using the image feature, we can combine with LSTM to see how these image features evolve over time. So LSTM give us a memory over time. And then using that, we can see how these cloth wrinkle under different motion. And from there, we can actually try different parameters to figure out what are the fabric material. What you see here on the left is actually a video collected at MIT for different fabric. And with our learning-based methods, we are able to extract the material. So what you see here is a real to sim transfer. We took the real input, the real fabric videos, and we transferred it to a virtual skirt of the same skirt but different material. And you can see when it's stiffer, the skirt flows differently in the wing. And this is kind of what we want. We call this a fabric cloning and material cloning. So this is the kind of things that we could do with design for clothes, for clothing and fashion. Another example is being shown here, where we also have different material directly from the input. We can clone it on this, virtual avatar. And now we change the material, the virtual avatar. It's still doing the same motion, but you can see the fabric material and the same dress, the same design, they move differently. And that is the power of this kind of material transfer through what we call a real to sim paradigm. We actually have applied this to a real product. This was actually my colleague at Amazon, and we captured him moving around wearing a t-shirt, and we were able to capture him moving around in the video so that we have the input video on the left. We were able to extract the fabric material and clone him on the right. So the avatar is on the right. We did not have all the facial feature yet, but the body was what we were focusing on, and the fabric material and the clothing is what we are focusing on. And you can see, there is a close resemblance of what we were able to capture on the body. And this is another perfect example of how we can actually enable virtual try-on this way. Now we have another example of a woman who is wearing a dress. And what we want to do is capturing that fabric material. So on the left, it was the input material. In the middle is what we capture. And then we can then transfer to a simulated cloth and move around. We did not capture the texture. But if we do, you would actually see pretty much there is no difference. This is a perfect example of what we have done. And we now actually have transferred it to a real Amazon t-shirt called the Merch by Amazon. And so you can see it on me. Our goal here was actually, we have a t-shirt like you see here. And it's the same person. You probably cannot tell, but it's actually different sizes of t-shirt. Small, medium, and large. Same person, but wearing different sizes of t-shirt. And you can see exactly how the t-shirt look on them. So this enables the customer to visualize how different sizes of t-shirt and dresses or a garment will look on their body. And this goes in and actually show you all the detail, but I'm going to skip some of that and just going to want to show you that once we have learned these garments and their fabric material, we could have the avatar move, and the try-on t-shirt will automatically wrinkle and they will fold naturally. We also have the print. These print have special material, and they also affect how the t-shirt move. And this is a perfect example that when you do this kind of virtual try-on, you can actually do a lot. Enable you to also have body wearing these t-shirt and undergoing different motion naturally. Um, and then these are different steps of algorithm. We are showing what was here is that if we change the 3D graphics print, the t-shirt would actually fold differently and would drape differently. And this is before and after. When we have very stiff, very heavy graphics print, the t-shirt actually drape very, very differently, as you can see. We have also show it in an application where we do a design of a two-tone dress. There are two different material. The blue material is stiffer and it's heavier. The white material is before. What you see there, it's softer. But when you transfer to the blue material, you see the stiffer material have different folds compared to the white. And you can have different design. We actually have two-tone dresses of a completely different design and they look differently on the body. So this was a test to see how different material and two different design can actually give you a different feel of what the garment will look like. So that was virtual try-on. But we have also extended this to autonomous driving. So the basic idea here is that we have a simulation platform that simulate all kinds of the environmental effect. We have the environment factor, we have the real world road network as the input, which are being then integrated into our simulator, which we can parameterize it. So we can actually change a parameter to create how the car will actually interact with the road and different elements and people and animals and other things in the scene. And then we can simulate our interaction. We also simulate a sensor such as the camera. And then we can create all kinds of scenarios. And we use these data to input it into our control module so that they can learn from these simulated data. And most of the time, as I already mentioned, when we have real driver collecting data from the real world, what they often miss is the accidental scenario. So we purposely simulate accident. So for example, we have an obstacles in the road and we will have this car drive through and learn. The first time we drive through, it will collide and then it will learn, okay, you don't want to keep driving straight because it will collide. And then you will try different trajectory. Every single one of these trajectory is being recorded so that the car can learn how far it can actually avoid the collision. And so this is the kind of learning process that we can have. We have also looked at all different simulation, all different kind of accidental scenarios and corner cases. There are about 37 of those. And these are just some example: running the red light, running the stoplight, turning and driving in the same direction or different directions, and rear-ending a vehicle in front of you, animal crossings, squirrel, deer crossing, and so on. And so what we actually did is simulating all these different scenarios in a virtual reality scenario. We put real driver in our virtual reality that was coupled together with the Unity game engines, and we have them kind of interact with these different scenarios. We set it up. We collect them. We also collect their personality. We have them take a personality test. We collect their driving and how that corresponds to different scenarios. So what we are doing here is we actually create fairly dangerous scenario, but they are created in a virtual reality environment. So no driver is getting hurt, but we know what kind of personality they are, and we know how they deal with different scenarios. So we are actually collecting information like this that are correlated to different personality. So here, just sort of kind of some of the examples that we
Following
created.
slides will be examples from the accident simulator along with trajectory prediction results from transfer learning.
So after it has the first collision, it will then not to drive that like before. And so these are kind of things that we have shown that we can actually collect these simulated accidents and use the information for training. So all different scenario you can learn and then you can collect. And here is an example of driving on the opposite road, and obviously you're going to run into collision. But this is exactly the kind of scenarios we want to generate. We can do this in the VR environment, but it's very difficult to do it in the real world. You don't want the driver to drive like
Following
this.
these
Okay, so in summary, is that we are using the VR driving simulator to create accidental scenario and put real drivers to collect information. We in fact have correlated personality with their driving behaviors, and we show that we can actually watch how people drive and figure out what kind of personality they are and how they might behave under different scenarios. These information are tremendously useful for autonomous vehicle to learn how to avoid some of these drivers under different scenarios. So going forward to the future, it's not just about human behaviors. We also have to deal with the nature. And so, again, a lot of these data that we collected are under, normal driving conditions, safe, typically good weather. The reality is, no, that's not how the real world we're going to have to work with. We may have snow, we may have frost, we may have fog. The lenses can be distorted. And when you're driving, you could have blur. You could have motion blur, zoom blur. You could have pixelation. You could have any other sensing artifact. So does your autonomous driving system have a perceptual module which is robust enough to deal with all these artifacts? And that's basically what we are doing. So what we are doing here, we are teaching the perceptual module how to deal with these all different kind of corruptions. We basically took real clean images batch. Then we augment them by corrupting the images through different process. And then we use these corrupted images that you see here. We use it for training. So you would know how to deal with these different kind of images. And this is the basic idea, is we use adversarial training on the corrupted images directly from the clean images. And we simulate different kind of corruptions based on the image attribute. I won't go into all the detail, but we basically are looking at blur, noises, the image attribute in terms of the color, the hue, the brightness, and the contrast. So those are some of the examples. And so we actually corrupt these image attributes to generate the data. And we show with this approach, our adversarial training outperform all existing technique. And it's able to ensure that not only we perform well on the original data compared to other approach, but we can also corrupt a single factor, it will do well. We can corrupt a different factor, it would also do well. And even if we have unseen scenario we haven't trained on, it would still do well. So this is exactly what we want. And we have actually done this kind of approach using a gradient-based
supplementary video for
approach, but we also
adversarial
have
training
developed
against image corruption.
we also have developed a gradient-free adversarial training. And just this summer, actually a week ago, we presented a new paper that is based on adaptive sensitivity analysis, that we can do this on the fly during the training. And I would encourage you to take a look at. Actually, just a couple of days ago, we presented at international conferences on machine learning or ICML on how you can make your perceptual system robust for image segmentation.
This is a supplementary video for gradient-free adversarial training.
And this is just sort of some of the example
Quality.
that kind of show you what we have tested on for autonomous driving. These are all different data sets that we have tested on. And we have, oops, sorry, I think I just went too far. Instead of going into the detail, the video actually going into the detail.
And directly affect image quality.
And these are different corruptions of
and
images.
HSV channels are chosen because both RGB and HSV spaces are frequently used to represent image color spaces. RGB represents 3 basic color values of an image. HSV represents 3 common metrics of an image: hue, saturation, and brightness. Other color spaces such as HSL or YUV have similar properties and are hence excluded from the study to avoid redundant analysis.
So we just show you what the single perturbation might look like And you can see on the right side, on the left side, it's a clean images.
visually.
And then on the two right columns are distorted images. And you can see
Here,
how they
we can
really
see
look
the visual
different.
differences and variations of RGB channel levels.
And those are the kind of images that we generate through simulating these noises and corruptions. And these simulated images, either on the left or right, are then being used to do adversarial training. And we have a weight. So amazingly, we don't have a real weather data, but by training adversarially on the single factor, which we call the basis perturbation, our perceptual module is able to deal with snow, fog, and frost and blur. And the reason is our single basis perturbation, a combination of them can create these kind of a natural effect. Everything that we see in the nature can be decomposed into these basis perturbation. So training on basis perturbation allows the perceptual module to deal with these different kind of corruption.
And here are some examples of what unseen perturbation data looks like. We studied the relation between the Frechet inception distance and mean accuracy.
So this goes on and actually talk about how we do this. We actually do this through sensitivity analysis. We systematically vary the input value of an image attribute. We see how,
while the vertical axes
we see how the output errors will change. And this is a concept actually originally introduced in control system, but we take it to the image perceptions and also steering of autonomous vehicle for learning system. And it works really well. You can see the numbers. Ours outperform everything else that's out there with this kind of approach. Okay, so I just want to kind of say, we have taken everything that you have just seen here, and we have also generalized it to things like integrating with neural radiance field to construct a real world model, and also introduce physical and functional and property and behaviors to drones and all kind of robots. This is a perfect example of videos. It's a monocular videos that was recorded, and we were able to we use these molecular videos to recreate the mesh representation, which we can reconstruct it directly from the videos. And then we can also alter the material property. For example, we can actually change how the ball might bounce. So a perfect example here is we can change the velocity. We can make a ball instead of going up and down, but to the left or to the right, as you can see here. We can also make it softer to the left or harder to the right. The ground truth is in the middle. So there is a tremendous potential when you can bring in the simulated physics into and combine it with a real world data like the video. You can achieve so many things. Now, going forward to the future, I would like to advocate that I think there is a tremendous excitement on generative AI. But one of the things that we really need to think about is, as we have already demonstrated in our work on autonomous driving, is AI plus safety. How can we ensure safe AI systems? And all the technique I just talked about here, the differentiable physics, it can help us inform physics in our simulation, in our learning. Data-driven simulation and reconstruction from video, we can use physical constraint incorporated into that to ensure that our system, our robot, will respect proximity, no collision constraints. And similarly, we can use this kind of simulation to incorporate it into training of autonomous systems, not just a vehicle, but also drones and underwater robots and many other AI-driven systems, AI empower automation. We could also use this kind of technique to help predicting how other humans might move and might drive, and therefore ensure that the AI system can work with the human side by side safely. And then there's the excitement. How can we go from sim to real to perform real world rendering using video diffusion technique? How can we use such a technique for adversarial training to ensure the autonomous system is always safe under all kind of weather conditions. So in summary, what I just demonstrated is this concept of learning-based approach using both the simulator and real-world data. And the simulated data were basically simulated using model-based approach, but we complement it with real-world data or vice versa. And this gives us a very nice unified framework to capture the interaction between vehicle and real human. And we were talking about human driver, but it's also applicable to pedestrian people who are walking. And allow us to control what we are doing in terms of automation through image-based analysis and simulated data, and also allow us to parameterize and supervise our learning, like what you have seen for virtual try-on. And it also leads to better generalization and transfer learning and far more robust learning system overall, and resulting in a safer and more robust and more generalizable AI systems. And that's the direction we would like to go. And we are continuing to working along this direction. One of the things that, as I already mentioned, is how can we improve the generalization? How can we incorporate human feedback, not just taking what they say, but actually watching how they move, and how they behave. Bring that, understand human intent, bring that into our AI system to ensure safety of the human. But everything that I talk about, a lot of it, it's all done in image space, in the visual domain. What we really need to move is toward multimodal learning. And that is to really think about how can we incorporate all different type of data, audio, visual, touch. And last but not least is how can we compute more but do less? Or actually, how do we learn more but compute less? Okay, so less data, but we learn more. Can we do that? And that's toward the edge AI, computing on the fly, on edge devices, on mobile devices, on small devices. It doesn't always have to be GPU cluster. Especially if you are doing space exploration, you will not have GPU cluster. If you're doing underwater, you may not have a GPU cluster. And those are the kind of thing we need to think about as we move forward to the future. These are sort of the scenarios where we actually are working, where we actually have a robot interacting with a human avatar. And so these are some of the examples. We also have videos here where we have mobile robot interacting with human, and they're walking around in the market, on the streets. These are the kind of scenario and operational cases we need to kind of think about. All right, and there's a tremendous potential. Once we learn a dynamic world, we could have AI agent interact with a real human naturally and coexist safely. Okay, I'm going to end right here and take any question.
Okay, thank you for the next talk. Any questions? Okay, Professor. I want to know, you just mentioned about the multimodal combination. So I'm wondering what's a promising framework in the state of art of the multimodal combination for the generating for the robotics embedding the intelligence in the
Right.
generation.
So we actually have some work that was published last year and previous year where we could have different modality of data, and we can use those. We also have audio and sound. So we have a building which is very transparent, very glossy, and if you just look at visually, you see through the wall because it's transparent, it's glasses. So we incorporated audio signal to tell us where the doors are, where the walls are, because the glasses are totally transparent. So the audio will bounce back. So that's one example where we can combine audio and visual together to reconstruct the world. We have also used different modality. We have LiDAR, we have RGB data. We can combine them together and we can do the learning offline with different modality. But on the fly, we only have camera data. So we call that auxiliary modality learning. And so basically, we have a secondary modality as a way to augmenting your main modality. And when we are during the test or the inference time, we only need one modality. And this concept can also extend it to different connected agents or multi-agent system. And that's how, autonomous connected vehicle can work in the future. So there's a lot of potential for multi-modality learning, but also multi-agent, reinforcement learning. That's another direction, is how different agents can collaborate and work together.
Oh, thank you. And I'm also wondering,
Okay.
For the simulation of this real world, or try to imitate the real world, we need quite a bunch of GPUs. So in the academy and the industry, now we can say there is a division between their interests. So how do you think about this?
So that's one reason that we have looked at differentiable physics, and we are computing the gradients. We are using the gradients to help us do much smarter sampling, so we don't compute as much. We use the gradient to help us learn faster. Like I mentioned, it's 10 to 1,000 times faster, and this is kind of where we need to go. So the differentiable physics is not just integrating the simulation with the learning, but it actually gives us a gradient for learning faster. And I think more technique need to come up. If we want to learn about the real 3D world, it's much more complicated and much more higher dimensional space compared to language. We need the gradients. And it's not only for physical world. It's also true. You can actually also compute the gradient of a policy. So the same kind of concept will also work there. We also have a paper at ICML just this year, and which is looking at how do we adjust the time step in building a world model, which we call the time-aware world model. And again, this was just published, a few days ago, appear at ICML. And this is something for us to think about when we have different dynamical systems working together. How do we take the time into consideration when we build the world model? And so we can do it much more efficiently. And that's the direction we are pushing. We are also looking at multi-scale sampling and many other possibilities. And those are exciting directions. As I already mentioned, we need to think differently. And yes, industry does have more compute, does have more GPU, but academic researcher hopefully will think differently, and we think smarter in the way that how we do the compute, so that we can accelerate, we can still advance learning and AI from a different angle by coming up with more efficient algorithm, by coming up with more effective architecture or new architecture that might compute things different.
Thank you.
Okay.
Any other questions for the?
Any other question?
Hi, Professor. I want to ask, when you do the research, and how you choose the data to enhance the efficiency or accuracy, or you can do the better research.
I think one of the things that I would argue is we need to start looking at sort of a reasoning and a context. So we don't really choose a data yet. We just simply say, okay, if we have missing data, how can we simulate? And so we are using simulation to fill in the gap with the real world. If we wish to continue collect the data from the real world, then some of the research in computer vision will be very relevant here. Is the problem called the next best view. That is a traditional and old computer vision problem. We need to re-look at the next best view. What is the next best view given what we have? And that means that we construct a model, and based on what we have, we fill in the gap and we decide where we want to capture the data. And so we need to do geometric analysis. And that's the direction I think we need to think about. Again, to bring it back to learning, combine it together, and really, think about how can we collect the data more intelligently. And that's the direction I would recommend people to think about and keep going. And, similarly for all different kind of data. If you need a physics data, you don't have it, think about how can you get it. And that's what we did. We have the visual data. From the visual data, we infer the fabric material. And the way we did it is by looking at the visual cue. And we understood that different fabric material wrinkle differently. So we actually look at a wrinkle density. This was automatically learned from the neural network. You figure out where the wrinkles are, the density, and you use that information to infer the fabric material. So those are the kind of things to really kind of think about as how do we design better neural network and better reasoning. It's not always the next token.
Okay, thank you.
Okay, you're welcome.
Okay, thank you, Professor. Very wonderful talk. So our section now is time is due. So thank you.
Okay, great. Thank you.